to be talking to you about the various advancements that we have made towards the development of brighter electron beams in my lab. And in the process, how we are uncovering some new, novel, interesting photoemission physics. First, to begin with, we asked what are bright electron beams, but even before that, what is an electron beam? Electron beam is a bunch of electrons all traveling in a similar direction. To put it a little more technically, the momenta of the electrons satisfy this condition where the longitudinal momentum in the z direction is much larger than the momentum in the transverse x or y directions. And what is electron beam brightness, or what is a bright electron beam? A bright electron beam is essentially lots of electrons packed together closely, all moving in the same direction. So this bunch up here, this cartoon shows a cartoon of a low brightness bunch, whereas this cartoon shows a cartoon of a high brightness bunch. Now, why do we care about electron beams? They are used in a wide range of applications, all of which are dependent, the performance of all of these applications are dependent on the brightness of the electron beam. They range from large kilometer scale particle colliders used for studying nuclear and high energy physics to scale and 100-meter, several meter scales X-ray sources to much smaller instruments used for electron microscopy and diffraction. I'll go through each of these in detail and show you how what impact does brightness of electron beams have on these applications. First is the X-ray free electron laser. These are gigantic machines over a kilometer long where electron beams are accelerated to giga electron volt energies. And once they're accelerated to those energies, the electron beam is made to wiggle. And as a result, it produces femtosecond scale bunches of extremely coherent X-rays. And these bunches of X-rays are basically used to make molecular movies of chemical reactions taking place. And as a result, they're useful in a wide range of fields, ranging from archaeology to chemistry, material science, and physics. There is a problem with these machines that they're just way too big. There's about 5 of them in the world, and the newest one costs about $1 billion, the one that's being built at SLAC National Lab. If we had brighter electron beams, turns out we don't have to accelerate the beam to these giga electron volt energies. About 100 mega electron volt energies can be sufficient to still get similarly coherent X-rays, and that would enable shrinking the size of these machines quite a bit to a few 100-meter scales, and you can think of putting one in a university scale basement. If we have brighter electron beams for the existing large free electron lasers, that would result in larger X-ray power, enabling new applications, and also larger photon energies, which would allow us to study more different kinds of materials using these X-ray free electron lasers. Then there's inverse Compton scattering, which is also a way to generate X-rays or even gamma rays, in which electron beams are accelerated not to giga electron volt energies, but a few mega electron volt energies. And instead of wiggling them in a magnet, they interact with infrared light and produce X-rays. We have here at ASU, we have the CXLS project and the new CXFEL project, where we are trying to produce such X-rays, femtosecond scale X-rays using inverse Compton scattering techniques. And in the CXFEL project, with some manipulations of the electron beam, we are trying to produce coherent X-rays similar to what XFELs can. Again, in these machines, the brightness of the X-rays produced is proportional to the brightness of the electron beam, and it's having a brighter electron beam is very useful for such applications. Then we come to electron microscopy and diffraction. Today, we have electron microscopes that can go to subatomic scale resolutions. Here is an image of image I took from a paper from Peter Rez, recently published, where they have studied the grain boundary of silicon to near atomic scale resolution. You can see the atoms, but they're somewhat blurry. But along with that, they have also taken the vibrational spectra of atoms and seen how atoms vibrate at different frequencies at the grain boundaries. Now, with brighter beams, we could make these images way sharper, truly go at the subatomic scale, along with obtaining vibrational spectra. Electron beams are also used to study dynamical systems, time-resolved microscopy and diffraction, where we have a pulsed electron beam and an electron pulse. A sample is excited by a laser pulse, and it's studied by electron pulse, which comes at a certain delay after the laser pulse. That's called a pump probe technique. And with today's brightest electron beams, we can study using such ultra-fast electron diffraction techniques. We can study crystal sizes that are small, like those of inorganic crystals. But if we were to study some big crystals like those of proteins, we would get a big blob like this. If we had 100 times brighter electron beam, you could get a nice diffraction pattern from a crystal, protein crystal like that of rhodopsin I've shown here. So generally, with brighter electron beams, we'll be able to observe phenomena at sub-nanometer scales and sub-picosecond scales with a much better spatiotemporal resolution. Then there's particle colliders. All of us know of the LHC, or the proposed International Linear Collider. In all of these electron colliders, the brightness of electron beams basically directly increases the luminosity of the colliders, which means you have more number of scattering events and you can study interactions with smaller cross sections. Or if you wanted some interactions which would take a long time to study, you'll be able to study in a much shorter time. It also enables new designs of colliders which won't have these damping rings, and that can reduce the cost and make allow us to actually build these colliders. It also increases the brightness or the luminosity of ion colliders, because brighter electron beams are used to cool ion beams and make their luminosity better. So both electron-ion colliders get better. So these are the various applications where electron beams are used. And I've just told you about how brighter beams will make them all better. Before we go into more details, I would like to talk about the temporal structure of electron beams. Electron beams have some sort of an internal temporal structure to them. They can be broadly classified into two types. One is continuous electron beams, which are used in most electron microscopes to measure steady state materials in their steady state. And then there's pulsed electron beams, which are used for stroboscopic ultrafast electron diffraction and microscopy applications, and also for X-ray sources, colliders, and single shot ultra UED or UAM applications. Here you need the electron beam to be pulsed to get the temporal resolution. And for these bigger machines to really accelerate electrons to mega electron volt or giga electron volt energies, you need pulsed beams so that you can use RF acceleration to accelerate them to these energies. Now, when it comes to continuous electron beams, they're almost always obtained from field emission tips, and in some cases also from thermionic emission tips, but it's also partly field emission. And in such cases, you have a very sharp tip and put in a strong electric field, and electrons are pulled out from a sub-nanometer scale area right at the tip. And that produces the brightest electron beams we know of. These field emission tips are by far the brightest sources in existence. However, they don't provide any temporal structure. Electrons are randomly emitted, usually in a Poisson distribution, and you can get a picoamp to nanoamp of beam current. Pulsing these is extremely challenging to a point where it's not really feasible, because the electrons are emitted because of a large electric field. It's not easy to just turn on and off a large voltage. There's capacitive effects. So generating a pulsed electron beam, we rely on photoemission. That's where photoemission comes in. Usually we have a train of laser pulses generating a train of electrons. And when it comes to pulsed electron beams, they can be classified again into two types. One is where you have a train of electrons where every bunch has a single to a few electrons. And in such a case, you don't, the electron-electron interaction between these electrons is not very significant, and you can pretty much ignore it. In such cases, the area of emission is largely dominated by the laser spot size that you shine on your cathode, and that's usually limited by the diffraction limit of light. For these applications, we need dense bunches of electrons with very large charge densities. So we have an intense laser pulse generating a intense bunch of electrons. And these this bunch of electrons, all electrons are very closely packed together, and they want to repel and disperse away from each other. And in such scenarios, the emission area is really limited by the charge density, or what charge density can be supported by the accelerating electric field. So if you need a certain number of electrons for your application, and you have a certain electric field that defines the charge density, and you need to have that big of a laser spot. Okay. Now, our goal is to increase the brightness of such pulsed electron beams. We are several orders of magnitude below the brightness we get from field emission tips, but field emission tips cannot provide us the pulsed nature of an electron beam, and that's what we are investigating in our lab. How can we increase the brightness of such pulsed electron beams? Before we go into explaining how we can increase the brightness, let's take a more detailed look at what is beam brightness. Beam brightness is defined as the charge density in phase space. It's really the current in the beam divided by what we call as the emittance, or the transverse emittance. The transverse emittance is the volume occupied by the beam in the transverse position and momentum phase space. And according to Liouville's theorem, the brightness of an electron beam remains invariant for Hamiltonian systems, which most linear accelerators are. So, which basically means that the brightness of the beam that you get at the source is as high as it can be. Beyond that, in the kilometer-long accelerator, there is no way to increase the brightness. It will only get worse if your accelerator is not designed properly. So it's super important to increase the brightness at the source. Now, what is the maximum brightness we can get at the cathode? As we saw, brightness is the current over the emittances in the two transverse directions. X and Y are usually equivalent. The emittance can be written as the RMS spot size times the RMS momentum spread, which we can also write as the RMS spot size times the square root of this quantity called as the MTE, or the mean transverse energy. This mean transverse energy is nothing but the kinetic energy of the electrons in the direction parallel to the cathode surface, or in the transverse direction. So it's simply half mv squared in the transverse direction. Now, for the case of for this case where we have a few electrons per bunch, where the space charge interactions or electron-electron interactions are not very dominant, the brightness is just proportional to current over the spot size squared and the mean transverse energy. Here, the spot size is usually a few micrometers. In many cases, it's even larger than a few micrometers, and it's limited by the diffraction limit of light. It's very hard to focus light down to smaller spot sizes. For large charge density applications, again, the brightness is current over sigma x squared divided by mt. However, the current is determined by the charge density, or the Coulomb forces, and it's basically a 3D equivalent of the Child-Langmuir law. And the current is proportional to the spot size times the electric field, which determines the current density. And therefore, the brightness is proportional to the electric field and inversely proportional to the mean transverse energy. So if we want to increase the brightness for such applications, we need a large accelerating gradient at the cathode surface. And just before the semester started, we had a couple of talks on how that can be done and what are the various efforts towards that. We are taking a different approach. We are trying to minimize this mean transverse energy. This mean transverse energy is largely a property of the cathode material, of the surface, and of the light that is used to extract electrons. So it's very much a materials physics, condensed matter physics problem. And that's where photoemission and materials physics comes in. Now, to set a scale, in most applications today, the mean transverse energy is a few hundred millielectron volts. And often when people design an accelerator, they assume that the mean transverse energy is going to be 500 millielectron volts. It's sort of a safe assumption. In most cases, people pick a convenient laser that they have. They use the most convenient surface to emit electrons from, which is usually the back plate of their electron gun, and they get whatever MTE that they get, and it's treated as a magical number that they obtain. And they usually assume it's 500 millielectron volts. And that's something we are trying to change. And we have done so quite a bit. So my lab, PBL, that's the photoemission and the bright beams lab. Over the last several years, we have contributed to discovering various factors that influence the mean transverse energy. And we'll take a look at what they are and what MTE really depends on. First, and in my view, it's the most important one, that's the excess energy. It's the energy difference between the photon energy and the work function, or really the excess energy that the photon provides the electrons above the work function. When they get emitted with this excess energy, they have the kinetic energy of photon energy minus the work function, or that's the maximum kinetic energy they can have. Some part of this excess energy gets converted into the mean transverse energy. So reducing mean transverse energy, very straightforward to do. Just change the wavelength of your laser to match it with the work function. And when you do that, the mean transverse energy gets limited by the Fermi tail of the distribution in the electron, and it gets limited to basically KT, the Boltzmann factor times the temperature. And if you want to reduce that even further, you cool your cathode, reduce the temperature, and you can get very small mean transverse energy. However, it's not as easy. Once you start reducing mean transverse energy, other effects show up. One of the most important ones then is the surface non-uniformities. If you have physical undulations on the surface, the accelerating electric field tends to bend and it gets a transverse component, which gives transverse kicks to the electrons. Secondly, if your work function over the surface is not uniform, you have a patch of some random contaminant stuck to your surface, even if they're at the atomic scale, they change the work function dramatically. And you can have patches of different work function that creates transverse electric fields, again, increasing the mean transverse energy. So to really minimize mean transverse energy, you need the smoothest possible surfaces, really atomically ordered surfaces. Then there is the band structure of materials. So when photoemission occurs, transverse momentum of electrons is conserved if you have an ordered surface. In such a scenario, if your electrons are being emitted from large transverse momentum states in the band structure, you get a very large mean transverse energy. So you need materials which will ensure that electrons are being emitted from low transverse momentum states. Then we have many body scattering. Sometimes electrons, the scattering cross-section of many body processes like electron, phonon, photon processes are quite large, especially in polarized materials. In which case electrons can absorb a phonon during excitation and get excited into large transverse momentum states, giving large mean transverse energy. And then there's nonlinear photoemission. Electrons can actually absorb 2 photons, even if they are close to the work function, they can absorb 2 photons and get excited to a very high excess energy. And that creates lots of problems, increasing mean transverse energy. So we tried to minimize all of these factors And our goal is to develop materials that satisfy all of these criteria to get smallest possible mean transverse energy. And we have set a world record for low mean transverse energy. To do that, first we had to develop instrumentation which could measure small mean transverse energies. And that's what we did. We developed this new energy analyzer, which can not only just measure mean transverse energy, but give us the complete three-dimensional energy momentum distribution of emitted electrons, or electrons emitted with very low energies, milli-electron volt scale energies. It works on the principle of time of flight. We have a time of flight detector and a cathode in this parallel plate kind of configuration. This time of flight detector measures the XY position at which the electrons hit it and the time at which they took to go from the sample to the detector. And from that information, we can find out what its energy and momentum was when it was emitted. So we use this instrument. We used an atomically ordered surface of copper. We had to prepare it in ultra-high vacuum using ion bombarding and annealing, several cycles of ion bombarding and annealing to get a really well-ordered surface. We cooled it using liquid helium to 30 Kelvin. And this copper 100 surface does ensure that its band structure is such that electrons are emitted from near the gamma point, so you don't have high transverse momentum states emitting. And that gave us a very, very small mean transverse energy, as small as we were able to measure 5 milli-electron volts at the photoemission threshold. To give you a picture, to remind you again, most photoguns use 500 milli-electron volts. So it's 2 orders of magnitude better than what's typically used. Not just that, we were also able to measure the energy spread. At threshold, we were able to measure very small energy spreads of 10 milli-electron volts, which is the smallest energy, which makes this the smallest energy spread electron source in existence, not just photoemission, including all electron sources. Yep.
How do you keep the surface of the
Great question. Wait for a minute. We don't. It lasts for not more than several hours. And that's one of the problems I'm going to be talking about next. And of course, this work was published as a physical review letter in 2020. Now, such a source would be fantastic for stroboscopic ultrafast electron diffraction applications where you need a few electrons per bunch. And it will also really enable ultrafast vibrational spectroscopy using electron energy loss instruments, and it will allow us to measure ultrafast phonon dynamics. Now, practical challenges. As you mentioned, first, vacuum conditions and preparations. As Will said, it wouldn't last for too long. Yes, it doesn't. And then there's also issues with nonlinear photoemissions for large charge density applications. First, we did solve this using a graphene-coated copper 110 surface. Coated with graphene, it's a really nice ordered surface. Once you put it in vacuum, it's very easy to prepare. All you have to do is anneal it to a moderate temperature. And we were able to measure the same small mean transverse energies from this surface. And it also lasts for a long time. It's not very stringent with regards to vacuum condition. So that's a fantastic development. The other issue is nonlinear photoemission. When we emit right at the photoemission threshold and further cool it down, we take a big hit in the quantum efficiency. That's the number of electrons emitted per photon. So to get a large charge density, we need to smack it with a very intense laser pulse. And that gives rise to nonlinear photoemissions. An electron absorbs 2 photons and comes out with a very large excess energy. And for the first time, we characterized this effect experimentally, and we were able to map out the transverse momentum distributions from intense laser pulses with different pulse lengths. And we can see all these nonlinear photoemission peaks in the transverse momentum distribution. If you see, these photoemission peaks are a couple of orders of magnitude smaller than the linear photoemission peaks. But turns out, since they come out at a way higher energy, these linear electrons are going to come out with milli-electron volt scale energies. These non-linear electrons, even with 2-photon emission, are going to come out at 4,000 milli-electron volt scale energies. So even if there's very few of them, they destroy your mean transverse energy. And we were able to characterize the mean transverse energy as a function of laser fluence, and also get what the mean transverse energy we could expect from this by extrapolation for various charge densities that are used in accelerators or used in some of these applications. And turns out, for the low quantum efficiency at threshold that we have 10 to the -9 or 10 to the -8, for these large charge densities, the mean transverse energy goes back into this few hundred milli-electron volt scale. So to really be able to obtain these small mean transverse energies in these large charge density applications like X-FELs and colliders, we need to have cathodes which emit electrons with a very large quantum efficiency at the threshold. So we need high QE cathodes to beat nonlinear photoemission. Well, turns out we have high quantum efficiency cathodes. There's a whole family of low electron affinity semiconducting materials, which are often used as cathodes. Alkali antimonides is a subfamily in this group. In these materials, there's some very interesting photoemission physics going on. Electrons are excited. In these materials, the band gap is very comparable to the vacuum level or to the work function. And electrons are excited into the conduction band from the valence band via light. And these electrons cannot relax back here because there are no states to relax into. So the electron-electron scattering process, which is a major energy loss process for electrons in metals, which really causes their quantum efficiency to be very small, is inhibited. And most electrons that go into the conduction band, if they reach the surface, they get emitted, and they keep lingering around in the conduction band for a long time. And that gives us a very high quantum efficiency from these materials. Now, alkali antimonides is a subclass of these materials, which has a high quantum efficiency as high as 10% in visible light. However, they have one issue, or rather used to have one issue. Their surfaces were very rough. They're usually grown as thin films, traditionally using a sequential deposition technique where people would deposit a thin film of antimony, then a thin film of cesium, and it would react on the surface, producing a thin film of cesium antimonide, or even potassium cesium antimonide. And that produced a very rough surface. So we put this rough surface in an electron gun. It creates transverse electric fields, increasing the mean transverse energy. We have come up with new growth recipes for these materials to develop a very, very smooth surface, a near atomic scale roughness for these materials. We modified the sequential deposition process into a co-deposition process where cesium and antimony are deposited at the same time, and that gives us a smoother film. And when we use lattice match substrates like strontium titanate for these growing these films, that gives an even smoother surface, a nearly atomically flat surface that you can see here. We recently characterized the mean transverse energy and quantum efficiency from these materials to an unprecedented detail. And right at the threshold, close to the threshold, we see near KT limited quantum efficient MTs. The quantum efficiency at these is significantly higher than what we get in metals. And if you are willing to compromise a little bit on the mean transverse energy, you can get a large 10 to the -3 level quantum efficiency, which is many, many orders of magnitudes higher than a metal. And we demonstrated a sub 50 milli-electron volt mean transverse energy with a 10 to the -3 quantum efficiency, which is again an order of magnitude smaller than the 500 milli-electron volts that's being used today. And now these cathodes are considered to be used in the next X-ray free electron laser, the LCLS2 high energy upgrade that SLAC is building. Okay, now these cathodes again have a problem. These thin films alkali antimonide materials exist only in ultra high vacuum conditions. Even in high vacuum conditions, they oxidize pretty much instantly. So it would be really nice to be able to discover robust, high quantum efficiency and low mean transverse energy materials. One approach towards that is to use the low effective mass of materials or low electron effective mass. In materials, if you have a band structure where you have wide bands or wide bands in the transverse momentum like this one, and you excite electrons with a certain excess energy, you end up getting electrons out with a large transverse momentum spread. Instead, if you are able to find materials which have very narrow bands in the transverse momentum, for the same energy spread, you can get a narrower distribution of electrons in the transverse momentum. And that can give you higher QE, low MTE cathodes. There are some very interesting materials, Dirac semi-metals or topological insulators, which have a Dirac point, which means the electron mass at that point is really zero. You have extremely sharp bands. And if we are able to emit electrons only from that Dirac point, we can get very small mean transverse energies, even at room temperatures. And some of these materials, topological insulators, are thought to be quite robust. So that could also solve our vacuum problem. Other class of materials are wide bandgap semiconductors. They often have very large bandgaps and also hence exhibit low electron affinity and a small electron mass. 3-nitride heterostructures can be quite interesting, something which we are exploring. There's also doped diamonds, which we'll be working on with Bob very soon. These materials typically emit electrons in the UV. Their band gaps are in the UV range, but you can develop heterostructures and alloys of these materials which have band gaps in the visible range and could possibly emit electrons in blue light. And those are some of the things that we are working on towards making robust high QE, low MTE cathodes. Okay, now that sort of brings us to the question. I've been talking about this conservation of transverse momentum, where electrons conserve the transverse momentum when they're emitted quite a bit, but is that even valid? Now, if you would ask many folks, they said, yes, it is valid. And in fact, it is the basis of angle resolved photoemission spectroscopy, which is a well-established technique where we use high energy UV or X-ray photons to extract electrons with energies greater than a few electron volts and measure the energy and angle at which these electrons have come out to obtain information about the band structure. And this technique relies on conservation of transverse momentum. So we know experimentally it's true in this regime. However, in fact, all of our photoemission theories have a very subtle approximation built into them. They call it the sudden approximation, which says when a photon excites an electron is emitted, it instantly stops interacting with the n-1 excited state surface that it has left behind. And experimentally in ARPES techniques, they have found the sudden approximation to be true. No one has ever seen it being violated so far. However, ARPES always uses electrons with energy greater than an electron volt or so. The electrons that we are interested in have 10 milli-electron volt scale electron energies, very, very small electron energies. They're going out extremely slowly. And if you consider the time required by an electron to move 1 de Broglie wavelength and plot it versus the kinetic energy, if you have a EV electron kinetic energy or greater, this time is less than a femtosecond. And in a femtosecond, it's usually things don't interact with electrons that easily. However, if you look at the same thing for a 10 milli-electron volt electron, you'll see it's 100 femtosecond time that it takes to move 1 de Broglie wavelength. And In that 100 femtoseconds, you can expect this electron, while it's getting emitted, to not only interact with the surface that's relaxing, but also with other phonons and plasmons inside the material. So whether the conservation of transverse momentum is valid at these energy scales, it's a very interesting question that we are trying to answer. And for the first time, we have the instrumentation, the energy analyzer that I described before, to actually measure the energy momentum distributions from such small energy electrons. And this could really lead to a new regime in photoemissions physics and perhaps even photoemission spectroscopy. Yep.
So typically I think about like
Yep.
Is it that sort of slow electron which will start to see the material that breaks?
Yes. So in a material, you have, that there is translation symmetry, but you have phonons. You have, when the electron is emitted, it leaves a n-1 electron state behind, and that all of that breaks the translation symmetry, and that's what these electrons are seeing. Okay. So far, we saw what brightness is and how it's related to the current and the emittance, the spot size, and the MTE. We saw how we were able to obtain a very small mean transverse energy. We saw how we can maximize the current without exciting nonlinear photoemission using these high quantum efficiency cathodes. But what about spot size? So far, we haven't really looked at it. And the small emission area, we saw that for these stroboscopic applications with few electrons per bunch, the spot size is limited by the diffraction limit of light. Now, can we go below this diffraction limit of light? Then for large charge density applications, it's not limited by the diffraction of light. However, we can create a transverse pattern in the electron beam, which helps mitigate the space charge interactions, and you can achieve higher brightness using such things. Furthermore, several applications require electron beams that need to be patterned in a particular fashion. For example, our compact X-ray free electron laser, we put in a lot of effort to generate a transverse pattern in the electron beam and then convert it into a longitudinal pattern. Can we make such patterns in the electron beam or in the light beam right from the cathodes? Turns out, yes, using plasmonic and photonic technologies integrated into the cathodes. This is a very exciting area of research that we have recently started in the lab, and we are already getting some very interesting results, which I'll show you right now. These are very recent results. They haven't been published yet, but they're very, very interesting. The first one is trying to focus light into a very small spot. We use these plasmonic spiral structures. So these are spirals etched into gold over a thin filament gold over a silicon substrate. When we shine 800 nanometers circularly polarized light on these structures, that light excites plasmons along the spiral edges, and these plasmons travel towards the center, and they interfere constructively at the center. And if you plot the field enhancement or the field of light as a function of the distance from the center, you see that the plasmon interference causes a very strong peak at the center. Now, this is 800 nanometer light, so you can't expect to get linear photoemission. However, if you have very intense light, you can get higher order photoemission. And in this case, we get fourth or fifth order photoemission, and the photoemission is proportional to the current is proportional to the power of the non-linear order of photoemission. So this, when it comes to the photoemission spot size, it becomes I intensity to the power fourth if it's a non-fourth order photoemission, and we get a very small electron spot of 100 nanometers full width half max. We were able to measure such a small spot in a photoemission electron microscope in our lab. And this is the tiny, tiny electron spot that we were able to get. If you measure the full width half max, it's 100 nanometers. Now, that basically results, we also measured the energy spread. Of course, the energy spread means transverse energy is several hundred millielectron volts because it's we're relying on nonlinear photoemission. It's not optimized for a particular excess energy. But if we converted both of these to emittance, it's emittance of 30 picometers, which is 50 times smaller than any other photoemission source. Which is extremely exciting. And we have recently demonstrated this reduced spot size and emittance via this plasmonic focusing. The other approach for getting a transversely patterned electron beam is using photonics integrated into the substrate of the cathode. We were able to develop a device where we had a silicon dioxide substrate with a small 400 nanometer waveguide of silicon nitride on top of it. And we deposited a thin film of alkali antimonide, cesium antimonide on top. And there was a grating coupler in this waveguide, which coupled the laser into the waveguide. And as the laser traverses through the waveguide, it excites electrons from the surface. And basically, we see the same pattern of the waveguide in the electron beam image. And we were able to measure this image, and you see the electron emission is largely confined to this waveguide. And here, for the first demonstration, we have used a millimeter size waveguide and about 100 microns in the other direction, but we can very easily scale it down to a micron or even a sub-micron regime, and it should still be valid. It would be the first way of patterning the electron beam to sub-micron length scales. So we have shown emission confined to this waveguide. Further, we also see this very interesting beating pattern at several hundred micron length scales. And turns out this beating pattern arises because of the interference of the transverse electric and transverse magnetic modes of light coupled into this waveguide. Another very interesting thing is this evanescent wave photoemission. It's a new mode of photoemission. Always, photoemission is either done in the reflective mode where light shines onto a surface and electrons come out, or in the transmission mode where you have a transparent substrate, a thin film of emitter, light comes from the back and electrons come out from the front. In this situation, the light is doing neither of those. Light is going parallel to the cathode surface under it, and it's exciting electrons via the evanescent wave absorbed into this emitter. So it's right in between this reflection and transmission mode of photoemission, and it's a new mode of photoemission. And it's also a novel way to generate arbitrary transverse shapes in the electron beam by shaping this waveguide to micron length scales. Okay, now a quick comparison to field emission tips. I told you these field emission tips are the brightest sources of electrons that we have so far. If you consider a scanning transmission electron microscope, you can get a spot size of 0.5 angstroms with 30 milliradians divergence, close to the state of the art that's possible at 300 kilovolts and 10 picoamps. If you translate that to emittance and brightness, it translates to an emittance about 1 picometers with a current of 10 picoamps, giving a brightness of the order of 10 to the 13 amps per meter square. Now consider photoemission sources. We demonstrated the smallest possible emission area, which had 100 nanometer full width half max, which converts to sigma x RMS spread of 40 nanometers. If we are able to combine it with the small mean transverse energy that we have demonstrated, the 5 millielectron volts, we get an emittance of 4 picometers, which is very close to the 1 picometer emittance obtained in electron microscopes. And to get the same brightness of 10 to the 13, we would need a current of only 160 picoamps. Is this possible? Yes, with a 10 to the minus 5 quantum efficiency with 30 microwatts of light, you would get this current. And very likely you can get this with high quantum efficiency surfaces. So if we want a photoemission source to beat the field emission tips, all we have to do is combine these three technologies that we have already demonstrated. It may not be trivial to do that, but I don't think it's impossible. And I think in the next 5 years, we'll probably be there. We really have the potential to surpass the field emission tip brightness. Another point here is the energy spread that we get from field emission tips is few hundred millielectron volts. What we would get from this is 10 millielectron volts. So if you consider what we call as the 6-dimensional brightness, it's way brighter than field emission tips. Okay, finally, we have developed all of these novel cathode technologies. How do we get electron beams out of those? Most electron guns today cannot use these novel cathodes. They use the back plate of the gun, which is typically polycrystalline copper, as the cathode. They just shine light on the back plate. It's convenient. No electron gun exists other than the one that we have. That's capable of using single crystalline materials at cryo-cooled temperatures, which is absolutely essential to get these low mean transverse energies that we have demonstrated. And those electron guns that can use some sort of novel cathodes, they are often used to power 24/7 operating facilities like colliders or exfils, and it's very logistically very hard to perform extensive cathode testing at these guns. So we developed our own electron gun where we can do that. It's a 200 kilovolt DC electron gun where you can cryogenically cool the cathode to 40 Kelvin. It's a very hard thing to do, have something at 200 kilovolts, at the same time cool it to cryogenic temperatures. It's a very interesting mechanical engineering problem. But we have successfully demonstrated that, and this is a first of its kind gun where we can also replace the cathode quite easily in UHV, and you have a wide flexibility in terms of the materials we can use as cathodes. You can see this cathode here. This is an alkali antimonide film grown on a molybdenum substrate, and we are using green light to get electron beams out of it. We also commissioned an electron beam line where we can measure the 4-dimensional phase space, so the 4-dimensional emittance, to characterize the brightness of these cathodes. And this is one of the first 4D scans, phase space scans that we measured. This gun can also be converted into an electron diffraction, ultra-fast electron diffraction instrument, which we plan to do in the next few years. So this is a picture of the photoemission and bright beams lab down in the Wexler Hall basement. This lab has been designed, built, and commissioned by my students in the photoemission and bright beams lab over the last few years. We've very recently completed the whole all of it in 2022. We have an MB style thin film deposition chamber where we typically grow alkali antimonide materials. We have a UHV atomic force microscope where we can study the surfaces of these materials. We have a photoemission electron microscope. We have this milli-electron volt energy scale electron analyzer that I told you about. And we have this electron gun. And all of these are connected in ultra high vacuum through this vacuum transfer line. It's a 30-foot long transfer line connecting all of these instruments. Then we also have a laser with a tunable wavelength. We can get any wavelength from 200 nanometers to 2000 nanometers with a push of a button. It's an amazing laser. Of course, that's a commercial laser system that's available. And we also have a helium recovery plant to allow us to do extended measurements at very cold temperatures. So in this lab, we can study thin film growth, atomic scale characterization, fundamental photoemission physics, electron beam physics, and very soon ultra-fast electron diffraction as well. Finally, this work would have been impossible without the fantastic, talented team of graduate students and postdocs, many of whom have recently graduated and moved on to various jobs in academia, industry, and national labs. And many are still active, and some of them have joined very recently. We also had many talented undergraduate students who have helped us enormously in doing all of this work. And finally, all of our external collaborators with whom I have several grants and collaborative papers. And in summary, we saw the new cathode science and technologies we have developed for high brightness, how we are investigating new photoemission physics, and the unique facilities that we have developed to really be able to make cathodes with unprecedented brightness. And finally, I would like to thank the Center for Bright Beams, it's an NSF-funded center for the funding, Department of Energy, both the high energy physics and basic energy sciences, and the accelerator development offices, the Moore Foundation and ASU for lots of help. With that, I would like to thank you for your attention.